Your next topic in grade 12 mechanics, which is more just like strictly more of a grade 12 type thing compared to, the distance and acceleration, speed, time, the kinematics, you guys did in 11, also in 12. You guys looked at, dynamics, the forces in 11, also in 12. In grade 12, you guys did a little specialization with the circular motion, and now we're going to look at the other kind of specialization for mechanics in grade 12, and that's starting to look at work and energy. So we're going to start looking at work and energy a little bit. Okay, now again, this heavily connects to what you guys have done with your kinematics and dynamics. It's just, once again, another viewpoint, another perspective, another way to look at things that makes solving certain circumstances, well, it's just another strategy to use, but not just another strategy to use, but also a great way to look at questions to solve them, which wouldn't be really much more difficult other ways. So it's a lot more efficient for certain circumstances as well. So really there isn't like a lot of new stuff in terms of the situations, just another way to look at it, sometimes better, sometimes people like it using work and energy. I often like using work and energy to solve mechanics type questions. It often works really well. There's a couple other special work and energy things we can look at as well. So we'll start with some basic type stuff. Now, of course, physics is often defined as the study of energy. So it's kind of nice that we're actually talking about energy for once. Well, the thing is, nobody really knows what energy is. And if you actually look up the definition of energy, it's often energy is the ability to do work. So just having energy is the ability to actually do work. But then if you look up the definition of work, it's often defined as the use of energy. So you sort of this cycle back and forth of these things just whipping around each other, which again doesn't really help define what it actually is. So it's more about for defined work, and especially we define energy based on our observations and what we can use it for, not what it actually is. So this whole energy thing, I mean, it's kind of tricky, but it's often defined based on what it actually does, or what it can actually do, or how it sort of appears and stuff like that. But it's kind of a tricky thing. But we're not going to worry about too much about all the theoretical crazy type stuff because it's kind of hard to wrap your head around sometimes. So we're just going to start with just the basic ideas behind work, of what work actually is. And of course, work is often defined as it's all about using energy. That's typically what work is about. Now, there's different ways you can look at it, but just mechanical wise, if you're going to use energy, basically what you need to do is you actually need to do something. Okay, and mechanically, when you're going to do something, typically you are applying a force on something to actually do something, to get it to accelerate, to get it to move. It all sort of anchors back to starting with a force. And that's actually a big part of basic mechanical work, is you actually need to use a force in order to actually do something. So not only do you need to apply force, but if something actually occurs, then it actually needs to move something. And that's sort of like the other part that kicks into it. You got to use a force in order to do something. And if you do something, you will then have some kind of motion. So they sort of link together. Now, if you can apply a force on something and it doesn't move, but then technically you haven't done any work because you haven't really changed the overall situation. You want to have some kind of overall change in the situation, or overall like the beginning and the end result. You don't really want them to be the same thing. So you want to use a force, cause it to do something, and have motion. Now, when you talk about having motion, you don't necessarily have to have a speed. That's not really what we're concerned about, because you could have something at rest, go from one place to another, and be at rest again. At all those points in the situation, it doesn't always have an acceleration, it doesn't always have a v, but it always has a location. So you want to look at the actual change in d for the object. Okay, so you have motion, which creates that change in d. And the reason we can't look at the speed is if you have an object at rest, and then it moves somewhere else, and it's at rest again, and you look from the beginning to the end, well, it did have v, but it doesn't anymore. But it does still have its change in D, which means work was actually done. So those are the two things that we typically focus on. And that's why you'll often see work as, basic definition, basic calculation is force times delta D, where you just multiply the force and multiply by the distance. So if you push with twice as much force, you're using twice as much energy. You go twice as far, you're going to use twice as much energy. They're both directly proportional. It's relatively straightforward. Now, the only thing that sort of kicks in a little bit is sort of like some of the stuff you guys have done previously, where you have, like a box or something like that, and you pull at an angle, and you guys know this. There's a force in the x direction, and there's a force in the y direction. Well, only part of that force actually goes towards moving it. It's just the Fx is the only part that is relevant to the situation. So what you want is it's the force that is parallel to the change in D. That's the key. So like in a case like this, it's not really the force at an angle, the force applied, it's just the force in the x direction. So that's why you'll often see the work expression often written as work equals FD cos theta. And that cos theta, just like solving, when you attach this to the force that, gives you the Fx, it sort of takes into account it's only the force that is parallel to the displacement that actually counts. So, I mean, there's different variations of it, but you'll often see FD cos theta or just FD if everything's parallel, but that's the basic way to calculate how much work is done. All right, and a lot of the stuff we'll do is just going to be parallel anyway. We won't really have to worry about the angle. Now, the other thing that we can look at a little bit is this expression right here. We got a basic three-term expression, and just like other stuff that we have done with three-term expressions, if you have a work distance graph, would look something like this. The slope of that line would be the force. Okay, so there's your basic type thing. So, your slope is going to be equal to your force that's actually being applied. The other aspect that we can take in, basic three-term formulas, other things you guys have looked at this year, if you have a force distance graph and, you're applying a force over a distance, the area underneath here, that area right there is going to be equal to the work that's done. The same way when you guys had VT graphs, the area was the distance, and you had AT graphs, the area was the change in V. Basic three-term formula, things like slopes and areas directly connect the same way as before. So, I mean, the basic way, work equals F times D. No big deal. But the graphical type stuff you guys have done with previous expressions, that also then applies to this stuff as well. And again, if you got a varying force and you got an FD graph, you just sort of get the area as best you can by chunking it up and finding out how it all sort of applies. Now, the other thing that typically kicks in as well, your basic type thing like this, typically the force that we're using here is going to be constant or average. The same way when you have DTV, the V has to be constant or average. The same thing here. The work equals FD. We assume, we generally will assume a constant or an average force is actually what we're going to be working with. So it's very similar to the other three-term formulas you guys have done in terms of like the slopes and the graphing and all that kind of stuff, and some of the similar ideas, the constant or average values, but just a different expression. Okay, so let's show you how this also connects into other stuff and see we've so far been looking at the work stuff. Let's see if we can incorporate a little more of the energy idea into this as well. So if we go back to generally what work is for, we've got work, and of course work is you want to try and use a force, you want to cause an acceleration, a change in V, which of course results in a change in D. So let's see if we can tie a few of these things together. Now, we've already sort of seen how W, we've been talking about those three quite a bit, but what about those two in there? Let's see if we can incorporate acceleration and change in V into this. Now, of course, if we have a change in V, that would imply that there's a V1 as well as a V2, so it actually can change. So what I'm going to do is I'm going to start with that part right there, the whole idea of having acceleration and a couple V's, and see if I can work around that and incorporate some of their stuff that's going on here. So what I'm going to do is I'm going to start with an expression you guys had previously, the whole v2 squared equals v1 squared plus 2ad. I want to start with that expression right there, because I got a couple of V's in there, I've got the acceleration in there, and I've got the D, which of course I also want for my work type stuff. That D comes in handy. All right, so let's see if I can incorporate then the other parts. I've got sort of like the last two parts in here already, but let's see if I can get to this and this. Well, if I want force, I mean, the basic force is equal to ma. I've got the acceleration in there already. So let's see if I can incorporate the force into this. Now, to incorporate the force, got the acceleration, I'm just missing the mass. So what I'm going to do is I'm just going to times the entire thing by m. Okay, now if I do that, I will get mv2 squared equals mv1 squared plus m2ad. And right there, as soon as I do that, these two things right there, well, that's force. Mass times acceleration, that is force right there. But I'm sure some of you have recognized this already. That means I've got force times d, and force times d, well, that's work. So just by incorporating m into that equation from kinematics, we've already incorporated pretty much the entire work energy type of idea into this expression. Okay, so I'm going to rewrite this a little bit. I'm going to end up with mv2 squared equals mv1 squared. That's the same. And I'm going to bring the 2 out in front. The m and the a give me f, and that times the d gives me w. So I can actually replace all of those letters with just work, something like that. Now what I'm going to do is I'm going to rearrange this. I am going to isolate work. I'm going to try and get work by itself. So I'm going to subtract the mv1 squareds from each other, and I'll divide by 2. And if I do that, I'll bring the w to the other side because that's what I'm actually solving for. You end up with mv2 squared over 2 minus mv1 squared divided by 2. And you get this. All right, now if I look at this expression, I've got a few things going on. Now, operation-wise, what's kind of interesting here is I'm subtracting here. I'm taking two quantities, which are obviously the same type of quantity because the variables are all the same. I'm taking them and I'm subtracting them. And I'm getting work out of it. And you guys know this already. You know, this from grade 9 science and other stuff. Work measures, of course, the use of energy, which, of course, is measured in joules. I mean, this is kind of old type stuff for you, but that's what we're doing over there. We've got these two things, mv2 squared over 2 minus mv1 squared over 2, and we're subtracting them. Now, if we're subtracting two values, and we're getting a measurement out of it that's a measurement of energy that tells me something about those two values. It tells me those two values must also be a measurement of energy. Otherwise, we couldn't subtract them to get an energy measurement. So these both have to be a form of energy. You can't subtract, you can't add or subtract values that don't have the same unit and get an answer that's different unit. They have to be, you multiplying and dividing is different, but you can't do distance take away time. You can't do speed plus acceleration. That doesn't work. When you're adding, subtracting, it limits pretty much everything, every term in the entire expression, all the stuff, all the chunks have to be the same measurement. So if I'm subtracting two things and I'm getting energy out of it, they all have to be energy measurements. And if I look at the expression, I am looking at an energy measurement that involves how much mass there is, but also it has to be moving. And of course, when you talk about the motion of energy or the energy of motion, that type of stuff, this is where the term kinetic kicks in. And this right here is the expression for kinetic energy. So that's exactly what that is. That's kinetic energy. So mv2 squared over 2, or this one, doesn't matter. Actually, let's get rid of the little subscript. That right there, that is how you calculate kinetic energy. Now, most people don't write it as mv squared over 2. Most people write it as, here's my EK, kinetic energy, as most people write it as 1/2 mv squared. But that's where the expression comes from. So it's basically taking the kinematics expression, incorporate Newton's second law, and you actually get the kinetic energy expression out of it, which is kind of mathematically nerdy cool. So really, what we have here, we've got that work expression. I'm just going to keep on going here a little bit. There we go. If I come over here, lowering out a room over there, I've got work. It's 1/2 mv squared take away. It's actually two kinetic energies actually being subtracted. It's kinetic energy 2 minus kinetic energy 1, which of course is the change in kinetic energy, which is another basic definition that you'll often see for work. Work is the change in kinetic energy. So if you don't change your kinetic energy, you didn't do any work. So that's, the whole motion thing where something has to move from one place to another. That's another way to look at it, is the change in kinetic energy. Something's at rest, goes faster, or something's moving, goes slower. Work was done. A force was applied to cause an acceleration, positive or negative, in order for the speed to change, which would then give a change in kinetic energy. Okay, so let's just do a practice question here to sort of show you how all this stuff sort of fits together. So here I got my sweet car, here's my road, and the car is going to drive along. Okay, so let's say we got a car here, and let's say the car is 2,200 kilogram car, and let's say it's moving around at 14 meters per second. And that car is going to drive across, go from here to here, vroom, right over here. And over here, let's say the car is now going, let's fix that. Now the car is going 35 meters per second. Okay, and let's say from there to there, the two distances, let's say that it went, let's say 62 meters from there to there. Okay, so something like that. All right, well, let's just start simple and find a couple things, because what we're going to do is we're going to look out for what's the force that the car used. Now, you could have done this previously. You could have done, use the v's and the distance to find the acceleration. F equals, like there's easily have done this even in grade 11, no problem. But we're just going to try using like the work and energy type of ideas. So to start with, I'm going to find out, since I got the mass and the v's, I can find kinetic energies. And of course, the car over here has got kinetic energy, good old 1/2 mv squared. And over here it also has kinetic energy, 1/2 mv2 squared. And I've got my masses, I've got my v's. It's really easy to solve for either one of the kinetic energies. So if I just multiply out the values, over here I've got about 215,000 joules of kinetic energy. And obviously on the other side, it's going, way faster. It's going to have considerably more. Here I'm looking at about it's 1 point something million, but we're not going to write it like that. There we go. So this is going to be 500 joules of kinetic energy over there. All right. So there's my kinetic energy at the beginning. There's my kinetic energy at the end. But it's not really about how much energy I have, it's about how much the energy changed. So if I found my change in EK just by subtracting them, I can find out that it gained a whole lot of kinetic energy. Just over 1 million joules of kinetic energy. So not only is that going to be my change in kinetic energy, this is then also going to be, that is how much work was done, because of course work is change in kinetic energy. Well then, if that's how much work was done and I've got the distance, I can relatively easily figure out how much force it was, because force is work divided by distance. So I'll just take that work that was done, just divide it by the 62 meters for the distance, and we're looking at around 18,300 newtons of force. And this would be, I mean, obviously in real life, there's no way this force would be constant, but this would be the average force used by the car to go from one place to the other place. All right, so that's how work sort of connects in with basic kinetic energy, and this is actually often referred to the whole change in kinetic energy equal to the work. This is often referred to as the work energy theorem, is what's often called, and just how when you do work, you apply a force to make the kinetic energy bigger or smaller, depending if you want to go faster or slower.